Hello Year 11 and welcome to our fourth video here for probability. We're looking at Venn diagrams and the addition theorem, which is not going to be super different to what we did last time. Just extending on that a little bit. So, Venn diagrams, a useful tool for analysing problems, particularly ones that have the words and, or, not in them. Maybe but as well. So, let's talk about mutually exclusive events and disjoint sets. Two events are mutually exclusive if they can't both occur at the same time. Right, so for example, if I roll a die and one of my events is rolling an odd number and another event is rolling a 4, well, they're mutually exclusive because if one of them occurs, it means the other doesn't. Rightio. We can call those disjoint sets. Okay, because they share no elements in common. As a Venn diagram, these are going to represent, on a Venn diagram, mutually exclusive events don't overlap at all. Okay, so they'll sort of look like that perhaps. And also we could infer that the size of the union of those two sets, of two disjoint sets, is equal to the size of one plus the size of the other. That's it. Because they're distinct like that, they don't overlap at all, the size of the combination of those two is the size of A plus the size of B. The intersection of those will be the empty set, because there are no elements that belong to both. That's disjoint sets, or mutually exclusive events. Here's an example. If a die is thrown, find the probability the result is less than 3 or greater than 4. Okay, those are two events and they're mutually exclusive because a number can't be less than 3 and greater than 4. So, probability of less than 3, 2 out of the 6. Probability that's greater than 4 will be, again, 2 out of 6. That's, 5 and 6. So, the probability of either of those occurring, right? The probability of A or the probability of B, the union of A and B here is 1/3, of course. 2/6 is equal to 1/3. 1/3 plus 1/3 equals 2/3. Okay, so that's the probability that the result is less than 3 or greater than 4. Okay, because they are mutually exclusive, I can find the two probabilities and add them together. Now, if my two events are not mutually exclusive, if they are not disjoint, then the size of the union isn't exactly the size of A plus the size of B, right? Because they overlap, and that overlapped region is going to be counted twice. So it's the size of A plus the size of B minus the size of the overlap, which is of course the intersection. And similarly for the probability of A or B, right? It's the union, right? The size of the union divided by the size of the sample space, which is the size of A plus the size of B minus the size of the intersection, all divided by the size of the sample space, right? Which, if you like, is the probability of A plus the probability of B minus the probability of A and B. Right. So, just to remind again, this symbol here represents the intersection and is associated with the words and, but. This symbol here represents the union of two sets, and that's associated with the word or. Here's another example. Card is drawn at random from a pack. Find the probability that the card is red or a 5. So or means we're looking for the union. We're looking for the union of red and 5. Now they are not disjoint sets. They're not mutually exclusive. And so I'm going to have to use that addition rule. So the probability of red is 1/2. The probability of drawing a 5 is 1 in 3. Okay, because 1 out of every 2 cards is red. 1 out of every 13 is a 5. So the probability of a red 5, and the probability of a red 5 is 1 in 26. Right, if you like, there are 2 red 5s out of the 52 cards, so 2 out of 52 or 1 on 26. That means that the probability of a red or a 5 is the probability of red plus the probability of 5 minus the probability of a red 5. Okay, and when I complete that expression there, I get 7 over 13. Okay, so that's the probability of drawing a red card or a 5. There is a 7 in 13 chance of doing so. And that makes a bit of sense because we know we've got about a 1 in 2 chance of drawing a red card, and a 5 on top of that. Well, there's only 2 extra cards we're adding to that, so it's a little bit more than a 1 in 2 chance. Here's another example. What's the probability of drawing a spade but not a 7? Now, there's a couple of words going together here. But is associated, is essentially equivalent to and. So we're looking for the intersection here. And not, right, ties us to the idea of a complement. So not a 7. Okay, we're talking about the complement of a 7 there, right? Anything that's not a 7. So I'm after the intersection of spade, right? And the size of that space is 13. There are, I don't care much for that. Oh yes, of course, sorry. There are 13 spades in a deck of cards, okay? 13 spades, 13 hearts, 13 diamonds, and 13 clubs. So the size of that space, there are 13 spades. The size of this space, not a 7, the complement of 7, how many cards are not 7s? 48 of them. So the size of this space, the size of that space. The size of my sample space is 52. So how many cards, right, belong to the intersection of spades and not 7s? Okay, how many spades are not 7s? Well, there are 13 spades and 12 of them are not 7s. Yeah. Alternatively, we could say there are 48 cards that are not 7s and a quarter of those are spades. So a quarter of 48 is 12. Either way, we can arrive at that figure. So the size of the intersection of spades and not 7s is 12. The size of our sample space is 52. So the probability of drawing a spade but not a 7 is 12 on 52, which is 3 over 13. Righto. Well, let's just go over those things that we've covered here. Mutually exclusive events, or disjoint sets, cannot occur at the same time. One precludes the other. The size of the union of A and B is the size of A plus the size of B minus the size of their intersection, or overlap. Okay, they're the two big ideas out of this. The next video up here is multi-stage experiments and the product rule. If you've got any questions about today's video, you know what to do. Jot them down so you don't forget. Ask me in class. And I look forward to seeing you then. Thanks, Year 11.